Hi, my name is Dominic Milioto. I'm here today to talk about how to map a double cover of the complex plane onto a torus. This is for educational purposes for students just beginning complex analysis. This is an education video. I'm hoping that students just starting complex analysis can look through this presentation and get a better understanding of how to integrate over a multi-valued function over a contour. I've noticed over the years students have difficulty understanding contour integration over multi-valued functions. And so I'm going to present it in a way that I believe just beginning students in complex analysis could follow. And in the process of this mapping, I'm going to create a normal Riemann surface in a way that Riemann originally intended these surfaces. Riemann's intention was to design a new surface and with a new coordinate system whereby multiple valued functions could become single valued functions. And we're going to do that with this square root function, a double valued function. I have a summary of what I'm going to do. I have the z-plane here with this matrix of points, lines, and I have over the z-plane the real part of this square root function that I'm going to use as the icon of the double cover. And I'm going to take the z-plane using that double cover and map it to the zeta plane. And throughout this whole slide presentation, I'm going to keep the same colors. The colors are going to go through, whereas this yellow surface here is going to get mapped to the yellow rectangle in the zeta plane, the same way for the green, the blue, and the red. And then I'm going to bend this double cover in the zeta plane. When I say double cover, I'm meaning this color-coded rectangle in the zeta plane. I'm going to bend it into a torus, maintaining the colors. I'm going to use the blue. The green is going to go to the green section on the torus. The red is going to go to the red, the yellow, and the blue. And also, I want to keep track, for a reason I'm going to show you later, this contour, this ramified contour over the singular point at z equals 1. You can see it if I kind of blow up the, you can see this contour. I have it color-coded. The yellow goes around to the blue. It wraps around the function to the green. Green turns to the red, and it goes back to the yellow. And I'm going to map that contour into the zeta plane with the same colors. The green part of that contour gets mapped to this green arc, and the red, and the blue, and the yellow. And I'm going to map that to the torus in the same color code. I have the blue part of that contour going into the blue section of the torus, the green, the red, and the yellow. And I also want to keep track to give us an intuitive sense of unwinding this multiple valued function into a single valued function. I'm going to keep track of this point. This little dot right here represents the point 1 plus I in the z-plane. And I'm going to map that point to two parts in this zeta plane that I have labeled, this little blue point that you could barely see here and a little red point here. And then I'm going to map those same points to this little blue dot right here and this little red dot right here. First, though, I want to look in a little more detail, and since this, I forgot about this one, since this is a training exercise for students just studying complex analysis, I want to give an intuitive sense of how are we going to map two copies of the complex plane into that little square in the zeta plane. And we can start with just simple functions. P of x maps the interval from 0 to 10 into the interval 0 to 1. They have the same cardinality. But intuitively, it looks like a bigger set of points into a smaller set of points. And the same way with this integral function. I could map the entire real axis into the unit interval. So it shouldn't come as a surprise that I could take half planes of the zeta plane, of the z-plane, and map that into a small rectangle. And we do this with a Schwarz-Christoffel transform. It's an integral transform. For every value of z, I'm going to integrate this integrand, and I'm going to obtain a complex value, c plus eta I. And I'm going to plot in the zeta plane that value. But first, I want to look at this double cover a little bit more. And remember, this is just the real component of the function. It gives us an intuitive sense for the integration. And that's another thing I want to emphasize. I find that students have difficulty understanding integration over multi-valued functions. So this real part gives us an understanding. We have here one cover right here, the yellow and the blue, and we have another cover here that I'm going to be integrating over. I'm going to integrate over each one of those surfaces in the complex domain. It's actually doing a complex integral, even though I'm using as the icon of this double cover this real part of the function. And one problem I find that students have with contour integration of a multi-valued function is, how do I know where the path of integration is going on this surface that can have multiple surfaces? And so, in order to effect that integration, I want to make sure that I integrate over an analytically continuous path over one of those color-coded half-planes. And I could do that by converting the integrand into its algebraic form, FZW, setting it equal to 0, and then implicitly differentiating with respect to t when I have z as a function of t. I obtained this differential equation. I set up an initial IVP problem. I start at the origin, z is equal to 0, and I define a function z of t. For example, if I want to integrate from 1 plus I, integrate from 0 to 1 plus I, z of t is just equal to t plus it. And we're going to track those 2 points that I spoke about. And this is some code I want to show you, and I would show the students also. I have the function defined here. I define z as a function of t. And I choose which surface of that multi-valued function I want to integrate over an analytically continuous path simply by choosing one of the roots to when I solve the function equal to 0. And for the blue sheet, I'm choosing root 2. Once I know that that root 2 is on the blue sheet, I'm going to set up ND-solve. I'm going to first compute the derivative, the implicit derivative with respect to t, set up ND-solve. I'm going to then integrate that differential equation in order to get an analytically continuous version of the function. So in that way, we eliminate branch cuts, possible implicit branch cuts that we might encounter if we just tried to integrate over the function itself in Mathematica. So I integrate the differential equation with ND-solve. I find the solution, and then I'm going to jump here, and then I'm going to integrate that analytically continuous solution with N-integrate. And I'm going to integrate from 0 to 1 plus I, and I want to run that code. Shift. Wait a minute, let's get it here. Shift, Enter. And just to show you what happens, when I integrate over that blue sheet from 0 to 1 plus I get this value, 0.49 plus 0.97. And I want to compare this to the built-in elliptic f function in Mathematica, just to make sure that my integration is correct. And in this case, I can do that. I'm checking it against elliptic f. I get the same value. And in order to do this mapping, I'm going to have to translate these values by plus or minus pi over 2 so that I can get the double cover rectangle. And I'm just showing the translated value. And just to get an intuitive sense, because sometimes students find this difficult, I just show the path on the real sheet. This is the blue cover. I'm integrating it from 0 to 1 plus I, and I just show the path here, 0 in red. And I want to do the same thing over the red cover. This time I'm going to choose the first root right here. Do the same kind of differential equation, integrate that differential equation, find the analytically continuous path over this red cover, and then I'm going to integrate that function. and I'll get the negative. It's the square root. And again, show it right here. Now I want to start plotting all of these points. I'm going to do this integral for each half plane of the Schwarz-Christoffel transformation. It maps the upper half plane to a polygon, which in the case of square roots, it's a rectangular polygon, and that's what I'm using here. And so I have here a color-coded map that we're going to build that double cover plot. So I have here zeta at blue. That means I'm going to integrate using that Schwarz-Christoffel transform from 1 plus I, get this value, and I'm just going to plot that point. That's the blue point. And then I'm going to integrate 0 to 1 plus I over the red sheet. And I'm going to get this point, and I'm going to plot them. And you can begin to already see how I'm going to unwind this multiple valued function into a single valued function. Because the blue and the red represent the same value of z, 1 plus I, but yet they get mapped to different places. And that's the same way for all the values of z. And if I do this mapping, that integral function, over the blue sheet for just a rectangle from plus or minus 5, I'll come out with this, and I'll get this plot. And these contour lines represent the horizontal and vertical grids that I had shown in an earlier video of the double cover. And I'm going to translate that into the first quadrant. Now I'm going to integrate over that, that cover over the red sheet. And I'm going to get this. And this is already translated. And I can do the same thing for the lower half plane over the yellow and the green sheet. And I get these. So we're starting to build that mapping. I'm mapping 2 copies of the complex plane. And even though, keep in mind that this rectangle, it only represents a very small section of the z-plane, like plus or minus 5. The entire remainder of the z-plane from out to infinity is in this little section here that I have not drawn contours. All the rest of it is in there. And also I want to keep track of this ramified contour that's wrapping around the singular point at 1 with those contours. If I map the blue section of that contour, I get that contour in the zeta plane. If I map the yellow, the green, and the red, and recall that ramified contour was a closed contour of winding number 2. It wrapped around the sheets twice because it's a square root function. And that's going to become important later on. And also I want to map the value of 1. The integral, the Schwarz-Christoffel integral is convergent at the singular points. And I'm mapping these points. I'm mapping 1, minus 1. K is going to get mapped there, minus K, and infinity. And that's how we create this double cover. And then later, I'm going to show how to just bend this double cover into a torus. And I have here a locator map, just to get a little experience. This, on the left side, is the value of z. And on the right side is the integral, the Schwarz-Christoffel integral, from 0 to that point. So if I move this red point right here, so say that's 1 point. I have the red at about 1 point I, 1 plus I. So the integral from 0 to 1 plus I gets mapped to this little red point right here. And you could see, if I move this, I'm going to move it to a higher imaginary number. Get higher and higher. It's getting closer and closer to that point at infinity. In the same way, it says students could experiment with this. And what I want to emphasize is I'm integrating over the blue and the red sheet. If I put them back, superimpose them at 1 plus I, keep in mind that they're getting mapped to different spots in this double cover. The same way with the green and the yellow sheet. Just something to play with. So I have this double cover. Now I want to bend it into a torus. How do I do that? I'm going to translate the double cover right here. This is my double cover. I want to bend that into this torus. And I'm going to do that with two different rotation transforms. First, I'm going to wrap it around in the alpha, in the latitude direction. And then I'm going to wrap it around in the latitude direction, in the phi direction. Now, how are we going to do that? And we want to make sure that when we bend it, the points end up where they should end up on the torus, based on the transformations of these equations. In order to map this double cover to the torus, we let C equals, well, I should have emphasized that this is the equation of the torus in the xy plane, x, y, and z, as a function of alpha and phi. And I'm going to map the points in the zeta plane, C and eta, are going to get mapped to alpha and phi. How I'm going to do that? Well, I'm going to let C equals phi, and I'm going to let this integral equation here, is n eta as a function of alpha, and we can even in the case where the torus has a radius of 2 and the tube has a radius of 1, we could even solve this integral exactly and get explicit expressions between, we have here, we're mapping the z plane, z, to the zeta plane, that double cover, and then we're going to map that double cover to the torus in terms of alpha and phi. So how are we going to do that so that these relations hold? How am I going to bend this cover so that all the points end up where they should end up when I'm done? So let's look at that. I'm going to use a rotation transform, a built-in function in Mathematica. You give it the rotation angle, the rotation axis, the center of rotation. And once again, I have the cover here. I have the torus, and I want to bend it in the alpha direction. I'm going to get rid of the cover and the torus, and I'm just going to set a set of points here. A set of points in the double cover, and if I take those points and map them to the torus based on those two functions I just showed you, how to map the zeta plane to the torus, I would get, they should end up there. If I do this right, they should end up on the torus. And also I have here, just to show students, this center axis. If I start rotating these points, it's just showing where the axis of rotation is. So if I start right here, if I leave it right there at the origin, axis of rotation is at the origin. If I take a point that starts at the location 3 on the x-axis, 3, 0, 0, and I rotate it by this many radians, that point would get rotated right there. And the same way with these other points where I have a factor of the rotation angle. It's from plus or minus 1, so I can get the negative and positive. But the important point I want to make out is if I just uniformly rotate these points, they're not going to end up where they should end up because of this integral. It's not a linear mapping. I have to adjust these points. I have to use a factor so that these points end up where they should, and I do that here. Once again, I have the torus cover where the points should be on the torus. And if I use that factor and rotate it, those points end up where they should. So now I know that I have the alpha rotation correctly. Now the C rotation is it's linear. C is equal to phi. Now what I want to do, I just want to take an arbitrary set of points in this double cover. And I'm using it as a parabola. Here's the cover right here. It's a parabola in the double cover. I want to rotate those points so that they end up where they should end up. If I rotated those points, they should end up right there. So first we use the alpha rotation with that scale factor, and then the phi rotation, and they end up where they should. So now that we have the algorithm working for an arbitrary set of points, I can now take the entire double cover, including all the grid lines, that ramified contour, the blue and the red point, and just bend it into a torus. And the point I want to make, and I want a better picture of this torus. I had a ramified contour in the z-plane that wrapped around the z-plane twice. As it wrapped around that singular point at 1, it now becomes a closed contour of winding number 1. It's winding around this singular point at 1, this contour. And we could use that as a basis for justifying applying Laurent's theorem to compute power expansions of this algebraic function, the square root function. But what I want to point out now is to realize what Riemann had in mind. Let's look at this blue point. Remember, this blue point was the integral from 1 plus I. And this red point was also the z value at 1 plus I. Now, if I associate that blue point, 1 plus I, as the value of the function, not the integral, just the value of that square root function over the blue cover at 1 plus I, and then I do the same thing with this red point, I associate that red point with z at 1 plus I plus the value of the function at the red cover, I can now define an entire coordinate system over this torus made up of points P, which are equal to the pair z and the value of the function over that cover. So now I have a set of points on this torus that I could define a function of these p's. F of p is equal to the w value, which is the value of the square root. And so now I have, so this value, this red point would represent z, 1 plus I, plus the value of the function over the red cover at 1 plus I. And this blue point would be z, 1 plus I, and the value of the function over the blue cover. So, and I could do that for all the points over the complex plane. 2 copies of the complex plane, and in that way, unwrap this multiple valued function so that it now becomes this function f of p becomes a single valued analytic function of the points p on this torus. And what I can do is I can apply Laurent's theorem. And I'm using this integral sign. I'm hesitant to use a new integral sign in mathematics. It's worked for me a lot. The integral represents a analytically continuous path, analytic continuous route over a ramified path around a singular point of an algebraic function. Now, in this case, it's very simple. It's just wrapping around the square root twice. But there are other functions, inverse of a 12-degree polynomial, that would have 12 branch surfaces segregated into 3 4-cycle branches. And in order to compute these power expansions, I would have to integrate over an analytically continuous path over one of those cycles. So it would wrap around 4 times. And in other functions, higher functions, will have multiple cycle types. I'll have a cycle type of 2. It'll loop around twice. A cycle type of 3. It'll loop around 3 times. And so this integral represents, we're going to integrate around this path. And if we do this, if we use this expression, we can actually calculate a Poisson series, a fractional power expansion for the function centered at the singular point at 1. Now, in general, there is a method that computes the exact values of the power expansion using Newton polygon. But I find it interesting that you could apply this using contour integration. And I want to compare that. I computed the first 10 terms of this series using these contour integrals. And I want to compare it to the value of this function, the original function, where I've included some constants, a. And to see that we get the same value, this value right here. And for those of you who are interested in more about this, I have a website. I'm going to click it here, called Algebraic Functions. And it goes over a lot of this. Plotting algebraic functions, applying Laurent's and the residue theorem. In complex analysis, you don't normally encounter using the residue theorem for an algebraic function, like a square root function. If I had a meromorphic function, I'd have a pole with a residue. Well, algebraic functions have residues also. And you could apply the residue theorem to algebraic functions using those expressions. And also have a summary of using Newton polygon to compute these power expansions. Okay. Thank you guys for coming.